So I just repeat, I mean, not only for Vera, but maybe for everyone. I shortly repeat what was the main thing. We started to study what happens in red matrix ensembles in which there is some feature that prevents from invariance with respect to rotation of the bases, and because of that, localization effects can be observed in such random matrix model. And the simplest one is so-called Rosenzweig-Forker model, in which you have just a full matrix of like Wigner-Dyson, but with small variance. So this gray gray background depicts size of the variance of the off-diagonal matrix elements. So they are small and become smaller as the size of matrix increase, and is the size of matrix. And there is a certain exponent which controls this decrease of the matrix element. And then there is a diagonal matrix elements which also fluctuate independently of each other, but the size of fluctuation is independent of the system size. So this is the model that allows to have both the localization transition and some new transition. And essentially the why this new transition may occur.
Sorry, Vladimir. So do you understand correctly that this rotational invariance is broken just because the diagonal is special?
Of course, because of this diagonal.
Yeah, okay, right. Thank you.
So, so the possibility of having some new transition and some new phase is because the localization criterion is written in this way. So the average modulus of diagonal matrix element multiplied by the size of the matrix should be in the localized phase, it should be smaller than 1 or even 0 in the thermodynamic limit. And this means that this gamma should be smaller than 2, should be larger than 2, and if it is larger than 2, then this thing goes to 0 in the thermodynamic limit, and this ensures that there is a localization phase. But then there is a different criterion of totally delocalized phase, which is called the ergodic phase. It is the phase like in the random matrix. And this criterion is different because it involves the second power of the average second power of the matrix element. And if we estimate this thing for the Gaussian distribution, then it will be the variance is n2 minus gamma and then times n, and so we have n to 1 minus gamma. And in order to have such totally extended phase, we should have these things greater than 1. And then it will be definitely greater than 1 at large n when gamma is smaller than 1. And so we have a gap between this phase and this phase, and this gap is filled by a new phase which is neither ergodic nor localized, and so we call it non-ergodic extended state. And this is the general reason why such state may happen. And then I computed here, I will not repeat this slide in detail, we computed here the distribution of wave function amplitude for such model, and this distribution appears to be power law. And when the distribution is power law, then the function f of alpha, which gives you the fractality of the wave function, it is linear in alpha, and because here there is the square root, then it is linear with the coefficient 1/2 in front of alpha. And then if we take into account also the dependence on the matrix size, so we will get such f of alpha. And this f of alpha in the new phase, in this non-ergodic extended phase, it looks like this. So this is this linear path with a slope 1/2, and then and then there is some rigid cutoff here and the rigid cutoff there. So it is such kind of trapezium, and if we have such f of alpha, we can compute the fractal dimensions, and in order to compute fractal dimensions, you should take the line with the slope q. If you want to compute fractal dimensions dq, you should have a line with the slope q and see where it is touching the f of alpha. So if q is greater than 1/2, it touches here, and when q is smaller than 1/2, it touches there, and therefore there is a different expression for fractal dimensions depending on whether q is greater than 1/2 or it is smaller. If it is greater, then as I said, the line touches the f of alpha here, and what we have to do to find the fractal dimension, we have to find where it intersects with the y-axis, and this point is minus tau q. And if you look at this geometry, then you will find that it touches at a point where at a point which is given by this expression. And then in order to find fractal dimension, you have to divide these things by q minus 1, and then you have a remarkable result that the fractal dimension for all q greater than 1/2 does not depend on q. And this situation we call monofractality. But if the q is smaller than 1/2, then it touches here, and then this tau q can be also found very easily to be this, and then of course there is a dependence on q. It must be there because we know that at q equals 0, the fractal dimension should be exactly 1. And so this is this result that we obtained in 2015, and this is a very important slide which is which explains you what is happening. So in this slide, psi squared is plotted at a given observation point as a function of the position of this point. And what you can see that there are plenty of small amplitudes, but then there are some number of of large amplitudes, which size is of the order of n to minus d. This is, this is smaller than 1, of course, but it is big compared to the average, which is 1 over n to the first power. And such points in the space where the amplitude is high they are distributed chaotically, randomly over the space, and this is what happens in the real space. But then we can do the following: we can fix here the wave function was fixed, and here we can fix the observation point R, but change the wave function, which is parameterized by the eigenenergy. And then we can also plot this psi squared. And what we can see also that there are, of course, plenty of small psi squared, but and there is some number of large psi squared of that order. But what is different from that plot is that all these high amplitude states, they are all compact in the energy, and if you take many realization, it is just one realization of the matrix. If you take many realization, then you see that they will be like a Lorentzian here. So already from this one realization, you can imagine how this Lorentzian appears. And in order to have some statistical analysis of that, what people do, people study the so-called local density of states. This is the sum of delta function, which is a usual density of states. But each delta function has a weight, which is the amplitude of wave function in an observation point. So this is the local. For this reason, it is local density of states, because it is it corresponds to some point in the space. And then one can compute the correlation function of such things, and if you plug in this expression into here, so what you will obtain that first of all, this thing because of integration doesn't depend on energy anymore, and secondly that there is a sum rule, and this is related with the normalization of the wave function. So this is the popular measure, and this measure is plotted here, and you see what happens. So there is first of all the level repulsion. So this correlation function falls down to 0 at a scale which is smaller than delta, mean level spacing. Then there is some oscillations with a period of delta. But then, if it would be a global usual level density correlation function, then we would have this level repulsion, then oscillations, and then it would be 1. But here what happens is that instead of approaching a constant at large omega, this function becomes a Lorentzian, so it falls down. And this Lorentzian is characterized by another scale. So this scale is mean level spacing, and this scale, which is much bigger, so it scales like n to 1 minus fractal dimension, and this is the typical thing for the situation where there is a mini band. So we have this scale is essentially the width of this mini band. To be precise, it is twice this width because there are two densities here, so there are in this problem there are two parameters of the energy. Both of them go to zero when the size goes to infinity. So, but they go to zero in a different way. So this goes like n to minus 1, and this goes much lower. For this reason, this is called mini band. Mini band because it looks like a band, but like a band of big amplitudes. But it is mini because it goes to zero when size of matrix goes to infinity. And so important, this is the same plot but in log-log coordinates. So here it is seen very clearly that you have the level repulsion, and then you have poorly visible oscillations with the period of delta, and then you have this fall down, which is 1 over omega squared. So this is 1 over omega squared. So there are two in between. There is almost a constant. So it looks like that. That here the local density of states correlation function looks like the global one. But then it starts to follow because for the global one, this mini band, it is the total band, and here it is really a mini band, and for this reason it starts to fall down. So this is this is the typical behavior in any problem if you find a mini band in such a problem. Then I studied so-called return probability. It is the average psi function at a given point at a time t if in the initial time it was a delta function. So when the wave function initially was created at one side, and then since it is not an eigenfunction, it starts to spread, and this tells you how much of this wave function remains on the initial side. So this thing we have shown that this return probability is nothing but the Fourier transform of this local density of states correlation function, and if you know this correlation function, then we know RT and vice versa. And so what is this for Rosenzweig-Porter case? It is an exponential decay. So there is some perturbative behavior here which is not seen, and then there is an exponential decay, and eventually, so this is the exponential decay, and eventually there is a saturation at the level which is n to minus fractal dimension. So then in between there is some overshooting. So it goes down, then there is an overshooting, and then it saturates as a constant. And as I said, this overshooting is what remains of the echo effect which I discussed in usual random matrices. What remains of it if we have a special diagonal. In fact, this feature is persistent. Now, if we know the decrement of this exponential decay, which is gamma, then we can confirm that this gamma behaves like n to 1 minus, like n to d minus 1, where d is fractal dimension. So this is exactly what is shown here. And so what is the difference between the usual Wigner-Dyson and the situation when there is a mini-band is that the decay is still exponential, like in the Wigner-Dyson case, but the decrement decreases and becomes zero in the thermodynamic limit. So if you increase the system size, so this decrement becomes slower, and slower. So then a new thing. So this is some picture which goes beyond this particular calculations for the Rosenzweig-Porter case, and it gives an entire picture of what happens. So what happens is the following. So imagine that you have imagine that you can see all the wave functions, which are fractal. But these fractal wave functions, they somehow are organized in a number of shells. So for each given shell, you have wave functions which are very similar to each other. So they are sharing the same support set. So of course they are not exactly the same, but they are very much similar. So there could be some little details which do not coincide, but all in all they are. This is one wave function, the other, the third, and so on. But all of them look very similar. And if we have an observation point for this local density of states, if we have an observation point which is inside of this support set, suppose I have an observation point here, then I will be able to see all of these wave functions, because the observation point for this wave function, the observation point for that wave function, and for all wave functions in this shell, they, for instance, corresponds to large amplitude. And then in the energy, all these wave functions will be seen as one mini band. So the mini band is basically the projection of in the energy space of what is happening in the real space. So if in the real space we have such shells of very similar wave functions, then in the energy space we have a miniband. And if we take a different observation point, so let's say not this one, but this one, again, since all wave functions are very similar in the space, so the large amplitude will be for all of them in this point. So because they are very similar, and therefore, if I change the observation point from here to here, then I will see the same support set in the energy, I mean, the same mini band in the energy space. But if I take the observation point here, where there is a small amplitude of all this function in this shell, I will not see this mini band anymore. But what I see instead, I see a different mini band in a different place in the energy space. And so what will happen is the following, that if I choose the point here where the wave function is small, then for some other shell, the wave function at this point, so somehow you should put this at the same space space region. Then if here the eigenfunction is small for all wave functions of this shell, it could be large for the wave functions of the other shell. So these shells are somehow interpenetrating in the space, so they are not separated so much in the space as in this figure. They are penetrating, but you know, my artistic skills did not allow me to show how they penetrate. But the thing is that if in some point you do not see a big wave function amplitude, then it means for this shell, then it means that for the other shell you will see big amplitude in this point. So the thing is how to find this shell. And then for this shell you will also have a mini band, but in a different place in the energy space. And if I take all possible observation points, so I am measuring the wave function globally, so not in one point here, not on one point here, but in all points. So if I have such a device that measures the wave function's amplitude everywhere, then what I will see is that I will see all of these mini bands. So this one, every one in between, and then the spectrum, which will be the global spectrum, because it is observed simultaneously in all the points. This global spectrum will not have such gaps, so it will be filled with many mini bands, and this will be the global spectrum. So this is the difference between the local spectrum and the global one. The local one when I observe in some point, and then I see only one mini band that corresponds to the shell in which there is a large amplitude at this point. But if I measure in all the points simultaneously, then I will have all these mini bands overlapping, and then I will see the total band. And
sorry. So the statement is that the mini bands that we have seen on previous lecture, they are formed by the states which like this belong to the same fractal shell, or like
Yeah,
they
yeah,
share
yeah.
the same support
Yeah,
set.
yeah, we
And
share the same
yes, yes.
support set.
And the question is why? So far you just stated, and I mean, okay,
no,
how
no,
can
I
you-
can tell you,
Yes.
I can tell you why.
I mean, this is
No, no,
like
I can tell
numerical
you
fact,
why.
or
I
what?
can tell you.
Yes.
So, suppose you have a piece of metal.
Yep.
You have a piece of metal, and then you know how to make all the wave functions in principle. So what you do, you say that it is a linear combination. It is a linear combination of wave functions at a given site. So how to make extended function out of functions localized in one site? It is to take a linear combination of all of them. And this is known as, this is known from general physics. Now, we also know that in such a piece of metal there is not one wave function, right? So you can do a different linear combination with different coefficients. But still you have the wave function which lives in the same piece of metal because all of these localized wave functions are involved, and all these coefficients are more or less of the same order of magnitude. So this is how in the energy space what one can say is the following, that if you have an energy of each side, suppose they are the same. So if there is no hopping which creates such an eigenfunction as a linear combination of the side function, then then there is a degeneracy. So there is a degenerate. All the energies are the same. But then I switch on hopping, and hopping produce the wave function which is a linear combination. And then what we know is that this degeneracy is split, and I obtain the band. Okay? This is how the band in the metal appears. Now, here, but you see, in this metal, all the wave functions share the same support set, because it is a total piece of metal. It shares the same support set. Like here. So the difference is the following, that there is some fractal, it is not a piece of metal, but a fractal in the space. And all these functions which are living on this support set, they are like the wave functions in the metal, but the volume of this metal is n to d. It is a restricted volume.
Yes. I mean.
So then, if I go, where is the other support set? And other support set somehow is close, is done in the following way. It is also some fractal thing, but it is avoiding intersection with this one.
Yes, exactly. And this is my question. Like, so this is a statement that two different fractal shells, the support sets of different fractal shells, they don't intersect with each other.
Yeah.
And where this statement comes from, is it some numerical fact, or
No, the fact is that you have a mini band because
Yes,
if you would, the reason you have a mini band is that it is like a band in the metal, but this piece of metal is the support set.
Yes, okay, so
If these support sets are intersecting, then they form one support set.
Okay.
So the fact that we have different mini bands tells me that there are many support sets which do not intersect.
Okay.
Because if they would intersect, we would have one mini band.
Okay, yeah, thank you.
So, and therefore, what we can say the following, that how many wave functions are in the shell. It is of the order of n to d. The number of it is of the order of the number of levels in the mini band. Okay, and this is the number of states in the mini band. But if I sum over all mini bands, I should have the total number of states. So this means that the number of mini bands is n to 1 minus d. But these mini bands cannot be observed simultaneously if you have a local probe. If you have a local probe, you have typically one mini band. For this situation with the Rosenzweig-Porter case. And I demonstrated you that, you see, there is one mini band and not many. Many mini bands appear when I have many probes in different points. If I have the probe that is global, I can simultaneously observe in all the points, then I will have an overlap of all these mini bands, and then the spectrum will be full. So this notion of mini bands, a notion of the shells, fractal shells, is the most important physical outcome of all these calculations with the example of Rosenzweig-Porter case. Because, you know, you can calculate whatever you wish, but if after the calculation you do not have any physical picture that emerges from these calculations, then these calculations are done, you know, in vain. Only if you have some physical picture which is supported by this calculation and is some sort of general output, then it is an important contribution. So now let's come to...
Sorry. Very final question. Do we know anything about the real space structure of the wave functions, of this like fractal shell?
No,
itself,
in
like
case
how is
of,
it
look,
distributed?
in case of, you know, this fractal shells
Yes.
is something which is my imagination, which goes beyond, goes beyond Porter, Rosenzweig-Porter. Why? Because the Rosenzweig-Porter gives you pretty in the space. The picture is first of all, it is one-dimensional space. And this support set is simply set of these points where the amplitude is high.
Yes.
So it doesn't have any specific structure for the Rosenzweig-Porter case. So,
okay, yes.
but if you have a more complicated theory where you can imagine something like, for instance, three-dimensional Anderson.
Yes.
In three-dimensional Anderson, you can you imagine such things, but how to observe it numerically? It is, you know, it is up to people like.
So it hasn't been done, and.
I mean, you know, how to observe it clearly. You should have a local probe, but how to construct this numerically or in a lab.
Okay.
So it is a different.
Okay. Thank you.
A different question. So I would not like to touch. And now there is a different model. So the model which is critical power law blended matrices. So in this case, you have all matrix elements independently fluctuating Gaussian variables. But the variance now depends on the distance from diagonal. So the variance here is, it is not only one diagonal which is special, it is the structure of all matrix, because the variance depends on the distance from diagonal. And this violates the rotation, basis rotation invariance. Now this situation, I would like to only say what is the difference between this situation and the Rosenzweig-Porter case. First of all, f of alpha. F of alpha for Rosenzweig-Porter case, as I have shown to you, it is made of the segment, a linear segment with the slope 1/2. So if you look at f of alpha here, so this b is the parameters that tells you how much fractal is the state. So if b is large, then we approach a Wigner-Dyson case, so the fractality is weak. If b is small, then the fractality is strong. And what you can see here is the following, that when fractality is weak, then it is f of alpha is more or less Gaussian, parabolic. But parabolic means Gaussian distribution of logarithm of psi squared. So it is log normal distribution. So at small b, the distribution is log normal. At large b, the distribution is log normal. And relatively narrow. At small b, look, what happens to f of alpha? F of alpha becomes, in fact, similar to the one that is in the Rosenzweig-Porter, because it develops some quasi-linear. You see, here it is a parabola, and this thing is more like this one with some rounded. Okay, so at small b, these two things converge, and this is the strong fractality limit, where all fractal dimensions are small. Now, let's see what happens with this local density of states correlation function. This local density, take it like an experimental fact. So it is very well seen in numerics. It could be, it could have some support from the theory, but only in limiting cases where b is large, then the sigma model works and one can have some theoretical insight. So, but the qualitative picture is clear. What you have level repulsion, like for the Wigner-Dyson, for the Porter-Thomas case, and like for Wigner-Dyson case. But then, then we have some fall down instead of instead of the constant for the global density of states correlation function. Then we have some oscillations with a period of delta. So we have all these qualitative features that we have for Rosenzweig-Porter, but when you go to quantitative analysis, then you see a difference. And the difference is that in the Porter-Thomas case, there was a fall, but this fall was 1 over omega squared. This is first thing. And second thing is that the prefactor was n-dependent, because gamma is n-dependent. So you have some power law, but with a power greater than 1. But then you have also the prefactor, which is n-dependent. Instead, in this case, what we have is that, again, there is a power law fall, but now the exponent of this fall is smaller than 1. It is smaller than 1. Now, the second feature is that the prefactor does not depend on n. So there are two features which I would say qualitatively, it's not simply quantitative thing, as I will show you. It is a qualitative thing, because the exponent is smaller than 1, and the prefactor does not depend on it. So when you have such a behavior, you can say by power counting what will be the Fourier transform of that. So you should integrate it, take d omega by omega minus d2, an exponent, and so by power counting you have d omega, then you have omega, so this unity cancels out, and what remains is omega to d2. But if I want to be in a time domain, then omega is 1 over time, and that's why return probability, which is the Fourier transform of that, it will be t2 minus d2. Again, the return probability for Rosenzweig-Porter was exponential, and the return probability for power law matrices, it is power law. This is related with the fact that the exponent is smaller than 1, because if the exponent is greater than 1, then the Fourier transform cannot be computed, as I said, so by power counting. So it should be taken. Seriously, and only when the power is smaller than 1 you can obtain the power law. If the power is greater than 1, then this thing is converging. The integral over omega is convergent at large omega, and this makes the difference. Because when the integral is convergent at large omega, the convergence of the integral is determined by this power law. But when the exponent is smaller than 1, then the integral by itself does not converge, and it converges only because of the oscillating exponent. So you see the difference. So if you have an oscillated thing here and omega 1 minus d2, then if I neglect this thing, there is no convergence. And the convergence comes only from here. And what does it mean? It means that it is convergent for omega greater than 1 over t. And this gives me the right to estimate this integral like omega to d2 and omega is replaced by 1 over t. Because the convergence is determined by these things. But if here is squared, then the convergence is determined by this thing. And then I cannot make such simple calculation because omega is not of the order of 1 over t, which is the main contribution to the integral. So this is again a qualitative difference between the power law with power smaller than 1 and power law bigger than 1. And it is best seen in the return probability. So now the picture. So this is, if you wish, the result about f of alpha, about local density of state correlation function. So there is also another important feature. Look, this power law, it persists down to delta, down to scale of delta. And if we compare it with the Rosenthal-Porter case, you will see that this power law is only for omega greater than gamma. And if omega is smaller than gamma, there is a plateau. And then there is level repulsion like in Wigner density. So this is also a qualitative feature that here the fact that it falls down after a scale of gamma tells you that such scale does exist, right? The fact that in this case this power law persists down to omega tells you that there is no such scale as gamma. So it is not a mini-band situation. Because if there is a mini-band situation, it should be plateau and then fall down. So what is then there? Now I will try to convince you that the local spectrum, when I have a local probe, is not like a miniband, but it is like a counterset. I will explain what is counterset. So this means the following: that you have, if you measure in one point, you see the levels everywhere in the entire band, but the spacings are very different. So there are plenty of small spacing, and there is the hierarchy of spacings up to spacings which are of the order of the full band. Now, if you have a global measure, if you have a global device which measures in all the points, then what happens is the same as in case of the miniband. So all such spectra are overimposed. So in one point I see this counterset, in the other point I see a different counterset. And then they are all overimposed. And suppose I color these counter sets by different colors when I observed in different points. So then after overlapping, I have a picture like this.
Sorry, it is counter set in energy space.
In energy
Energy
space.
space, yes.
This is an energy
Energy
space.
space.
Because it is local density of states as a function of the energy. So this is the situation. So this is the local spectrum observed in one point. This is the global spectrum. When I observe in all points simultaneously, then I see all these colorful counter sets. And if I remove the color, then it will be just gray spectrum. So this is the difference. The local spectrum in the Rosenzweig-Porter is a miniband. The local spectrum is in this. So this is the statement now, and I will try to convince you that it is correct. So this is the picture. Now, you see, one thing I can say immediately. The thing is that when there is an hierarchy of the spacings, big spacing, small spacings, then there is no a definite parameter gamma, which is the miniband width, and therefore this power law, which reflects this hierarchy of the gaps, it persists down to mean-level space. Now, if you look at this picture, so the wide distribution of the spacings, you start to suspect that in fact this distribution is a power law. And if I say that my local spectrum is a sequence of levels with some spacing, and the spacings are independent, so I may have big spacing suddenly or small space. If I say that they are independent and not correlated, and that the distribution of all spacings is what is called identically independent, identically distributed. Independent, identically distributed. Then I will convince you that if we have a power law distribution like this, it will reproduce the observable result like this. So the observable result is that down to delta there is a power law, and the power is smaller than 1. So I will show you now that if I assume that the spectrum is independent, identically distributed spacings, and distribution of spacing is like this, then I will have all the features of this thing. So now I want to say a few words about the counter set. So the counter set was invented by Cantor, as you may, and it was a purely mathematical construction, and maybe it was the first construction with a fractal structure. But for us, not so many facts are unnecessary. So first of all, what is the textbook counter set? It is not a random counter set, this is a textbook counter set. So take a segment from 0 to 1, and then remove a part in the middle, which is 1/3. Now, in the remaining part, remove in the middle 1/9. And then in the remaining part, removing in the middle 1 of 27. And so on. This is the textbook Cantor set. So the spacing between these intervals, I would not say spacing, it is in intervals, then there is one interval with the length 1/3, then there are two intervals with the length 1/9, 4 intervals with the length 1/27, and in general, so many intervals with the length like this. Now, let me come from this to some spectrum. So what I do the following. I put a line which is in the middle of this white area. So here there is this line. Now 1/9 is this line, then again this line. So in the middle of each white interval I put a level. And then you can easily see that there are two spacings which are 1/6. It was 1/3, I divided by 2, the spacing is 1/6. Then there are 4 spacings with 1/18, 8 spacing with 1/54, and in general 2 n spacings with such size. Now you see that the size of the spacing on each on this step is such that 2 times spacing is 1/3 So this is the general size of the spacing between such levels. And now I want to compute what is the probability to find spacing smaller than to find spacing greater than some delta. Now, what means greater means that this is the probability to find small spacing starting from delta I down to the smallest. So this means that you see the number of spacing increases when spacing itself decreases. So what I'm doing, I'm summing how many spacings are which size is smaller than some delta I. And this is simply to sum this thing from the step I, which corresponds to big spacing, from the step I downwards, and up to some n, because I have a minimal spacing which is equal to the mean level spacing in the global spectrum. So I suppose that the minimal spacing is 1/n, where n is the number of levels in the global spectrum. So what I'm doing here, I'm summing all these numbers, up to the minimum spacing, and divide by the total sum, which starts from here and up to the minimum spacing. So this is a geometric progression. You can easily find the result, and the result is like this. So of course, if I want to find the probability to find small spacing, then if spacings are very small, this probability is close to 1, because there are many spacings small and fewer spacings large. So this is the result of this summation. So now I rewrite it in the following way. So this unity remains, then 2 to minus n remains, and then there is 2 to I. 2 to I. And I will, this 2 to I say that it is exponent of logarithm of 2 times I, and this I express in terms of delta. So logarithm of 2 delta divided by logarithm of 3 is minus I. So this I is logarithm of 2 delta divided by logarithm of 3 and minus. And then what I have here, I have 1 over delta, which is minus and this logarithm. And then in front, in this exponent, will be logarithm of 2 by logarithm of 3. So there will be things like that. And this, what I computed, is the probability to find delta which is smaller than delta I. So in terms of the probability density, this thing is given by such an integral, and this is the probability density. So if this delta I goes to 1, then so the thing is that this power law distribution which I proposed, it must be cut off for small delta of the order of minimum 1, and for large delta of the order of the total bandwidth. So there are 2 cutoffs here. And so when so when I put here the upper cutoff, then this integral should be equal to 1 as the probability conserved. So then what I should do, I should differentiate. I have 2 expressions. One of them is this, which is calculated directly how many spacings of which size I have. And the other is just a definition of the same things in terms of the probability density. So let me differentiate with respect to delta I. If I differentiate this with respect to delta I will get P of delta I. If I differentiate this with respect to delta I will get sign minus, of course, and then this is a constant which involves this thing, and then when I differentiate, I will have this guy also goes to a different constant. But important thing is that the power of delta will be this one plus one when I differentiate. So this means that the probability density to find a spacing in the regular Cantor set is exactly like this. So there is and this it is greater than 1, and this additional part is logarithm of 2 by logarithm of 3. So this is, by such calculation, I find this P of delta, and this fractal dimension, which I should put here, is logarithm of 2 by logarithm of 3. This is just the result of this calculation. Of course, this logarithm 2 of logarithm of 3 is because it was a particular Cantor set when I removed 1/3, and that is why this fractal, specific fractal dimension. If I would do a bit different thing, I would, let's say, remove 1/4 and things like that. Then I can have different fractal dimensions, but the power law will be there. So the important thing is that there is a power law with a power greater than 1. So this is one of the reason to say that that this is a Cantor set. But now it is a random Cantor set because delta are not correlated. In this situation, deltas are correlated. But the way the probability of delta depends on delta is exactly like for that proposed random Cantor set. So this is one fact. Then the next fact is the following. Let me compute what stands for the local density of states correlation function models by this Cantor set. So let me introduce a counting function, which is m is the number of levels in the local spectrum. M is the number of levels in the Cantor set, and this is simply the integral of that. So instead of delta function, I put theta function. Now this counting function looks like that. It is like steps, and the gap is now a plateau. So there is 1/3 was a white region. Now instead of the white region, there is a plateau. Now I do the following calculation. I take this thing with a delta function and take the sum, and then I make sort of averaging. So what is this averaging? It is simply the integration over energy. So that means that this picture may be shifted by an arbitrary amount, and I am averaging over this shift the product of these two rows. So this, I don't want that, since initial interval was from 0 to 1, then I have to restrict my energy in order that something remains here, that I don't go beyond this, and so it is simply to have something non-zero. I have to put this into.
Sorry, Vladimir. In the definitions of C and rho, it should be just E without omega, right?
No, it is simply.
What is omega here?
The rho is
yes,
derivative of C.
Yes, but what is omega in the definition of C? What is omega?
No. Here, sorry. Here I should erase this omega.
Yeah,
There's
okay.
no omega.
Yeah.
I mean, I just copy paste. So this,
Okay.
This should be erased.
Yeah, thank you.
There is no omega here.
Mhm.
Thank you. And then there is this relation. So I put this thing, and here omega appears because I make a shift. This
Yes.
row is from E plus omega over 2. This row is from E minus omega 2, and then I average over E with a plane distribution. And then, in order to find, in order to express everything in terms of C, so I have to simply differentiate 2 times with respect to omega. So when I differentiate 1 time with respect to omega, I get rho out of C from here, and then if I differentiate the other time, I get rho from here. And since there are different signs, here the sign will appear, and also this 2 is amounts to 4. Why I did this in terms of C? Because numerically calculate something with delta function is impossible. I mean, numerically it is impossible. Whereas with a step function, it is pretty much possible. So what I did, I simply took this this thing, plugged it into here, and numerically integrated with respect to E. And what I obtained, I obtained almost the straight line, and down to the minimum omega, which is mean level spacing. So here, when omega approaches the mean level spacing, it starts to have some structure. But for omega much greater than mean level spacing, it is very much like straight line in log coordinates. So this means that it is a power law. And now what I do, I differentiate, I plug it, this f is just this integral, and then I differentiate it with respect to omega. And the result of this differentiation, you see here there is 1 plus fractal dimension, which I have already specified when I computed the distribution of spacing. It was 1 of fractal, plus fractal dimension. Then I have to differentiate twice, and then it will be omega fractal dimension minus 1. Here is again misprint, so there should be 1 minus ds here. And you see what I get is exactly this power law, which goes down to delta, and the power is 1 minus d2. So for numerics gives for power law-bended matrices, and also in the critical point of Anderson transition, it gives 1 minus d2, and this is known as Churchill-Ansatz. John Churchill that suggested in 1990. And so what I obtained by such construction, I obtained this power law. I mean, here there should be 1 minus ds, and ds is this. So I obtained this power law, but this was the fractal dimension of the Cantor set, because what I did, I counted this the probability of spacing. So this is the probability of spacings, and therefore it is the fractal dimension of the Cantor set, like this. And but what stays in the Churchill-Ansatz, it was d2. Therefore, I have to come to conclusion that if this picture is correct, then the fractal dimension of the Cantor set should be equal to fractal dimension d2, which is the characteristic of wave function in the space. So a very non-trivial thing happens, that the characteristic of the wave function in the space is translated to the characteristic of spectrum in the energy space. So it is a deep connection between the real space and the energy space. But this was for the regular Cantor set, which is from the textbook. And now what I do, I will make the same calculation, but for the random Cantor set. So what I do, this is a different calculation in fact, but the calculation of the same quantity. So what I want to compute, I want to compute this thing, which is the what is called C local, but in fact I am doing that just using the following, just using this assumption and that spacings are identically independent, identically distributed quantities. Now let me make this calculation. It is a very simple one. So what you do, you compute the same object like for the local density correlation function, but I presume that I take into account only levels with high amplitudes. All levels with low amplitudes I somehow discard. And this is something which we are doing now with Simon and Lev Widmar, just numerically. This is the definition after integration. And now I take the Fourier transform, and this is the what is called spectrum form factor. But these are the levels which difference is the sum of the spacing between the level J and level I. So the difference in the energy is expressed through the spacings. And now what I have to do, I have to compute exponential of that and average it. So when I put it here, I will have exponential of the sum. Exponential of the sum is a product, right? Exponential of the sum is the product. And now, if I have all spacing independent, then averaging the product, I can average each term of this product. Because for independent variables, averaging of product is the product of averages. Okay? So I have to average each term and raise it to the power which is I minus j. As simple as that. But here, of course, I took into account first that all spacings are independently fluctuating, and second, that they all have the same distribution. And so I will have this object in terms of which I can express everything. So then I have to plug this object into here and sum over I and j. You understand that this sum is some simple geometric series, in fact, and therefore this sum can be easily done. So I introduce this average like g of tau, where g of tau is given in terms of the distribution function. Then the distribution function is, as I said, it is power law cut from below and from above. And then when I compute all this double sum, each of them is some restricted geometric series, then believe me, I'm getting the result like this, where m is the total number of levels in this in this Cantor set, which is supposed to be n to d2, but this is at the moment I don't need it. So this is simply the sum of geometric series. It looks a bit cumbersome because there is a double sum and there are some restrictions from this absolute value and so on, but it is easy to do. So I have this expression, and then if I put this g of tau here, I find the spectrum from factors. So one can do some general statement after analyzing this expression. First of all, this g of tau, when tau is 0, it is 1, because it is just the conservation of the probability. So 1 minus g is a small value. And then what I can see is that the main contribution when tau is small, and small means this restriction, will be this big formula reduces to such simple one. And then if we have power law distribution of P of delta, then this 1 minus g is a power law in tau. And then I have to plug it into here and I'm done. And so what I see that that this spectrum form factor is T2 minus dx. It is exactly what was observed for power law matrices when dx is equal to d2. And then there is also the total number of levels, and when I do the Fourier transform of that, I will obtain this thing. So I will obtain delta by omega 1 minus ds and the prefactor that depends on it. And we know from numerics, from some analytics, that this thing for power law-bending matrices, first of all, has a power which is 1 minus d2. And second, that it doesn't depend on n. And if I put ds equal to d2, I do both things simultaneously, because first, the power will be 1 minus d2, and secondly, since delta is 1 over n, I will cancel this factor. So one assumption that ds is equal to d2 gives you two things fulfilled. So this is the calculation that says that the random counter set gives you all the features of the situation for numerical situation and some analytical situation for power law-bending matrices, and this is the last slide. There is a good example when this P of delta has the form like this. So it is a power law cut at delta of the order of minimum one, but this function, which is called stable distribution, this is very special function, because it is a distribution that after convolution gives the same distribution. So you may do many convolutions and you will have the distribution of the same form, and therefore it is called stable distribution. And known distributions such as Lorentz distribution, such as Gauss distribution, they belong to this family. Then the second important feature of that distribution is that the Fourier transform of this P of delta has a very simple form. So it is a stretch exponent with some phase which makes it one-sided. And then you can put this thing into this huge formula and plot what happens. And this is the result. So you see